Welcome to Applied Engineering channel. Today we will dive into one of the most important parts of HVAC system modeling, that is experimental validation. We are going to see how simulation results from cycle DHX and compare against the real experimental data. So validation is a crucial step before moving into optimization. So first I will explain the stepwise approach of the validation procedure for you. Then we will dive into our simulation software. So stick around because by the end you will see how theory meets the reality. So we will start with our 134A as the baseline and then we will validate the model against the experimental data. And then we will optimize it for other low GWP refrigerants. So this work is explained in IJR, that is International Journal of Refrigeration research article, as well as in NIST document, which I will include in the description for your reference. So what is validation? Validation simply means checking whether our model is telling the truth. In other words, does the computer prediction match what we actually measure in the lab experiment? Without validation, even the most advanced simulation is just an assumption. So in our simulation or our validation, there are some performance metrics. So in our case, the performance metrics are the cooling capacity, COP, pressure and temperature, or compressor efficiency. So if the simulation predicts the cooling capacity, COP and pressure within a small margin of error, we can trust the model for further use. So why validation is important? Think about it in this way. Imagine you build a car engine simulation and it shows fantastic performance. But when you build the real engine, it fails miserably. So that's what happens without a validation. So validation ensures accuracy of the model, reliability for future designs, confidence in optimization decisions. So theoretical models often ignore the real world inefficiency, but by validating we make sure that the software accounts for all these effects. So this step is critical before using the model for system design or for other refrigerant comparison. Cycle DHX is a semi-theoretical model that simulates the performance of vapor compression cycle with forced convection heat exchangers for specified temperature profiles of heat source and heat sink. In this study, we validated cycle DHX using experimental measurements from a small, less than 4 kilowatt capacity heat pump test apparatus operated in the cooling mode. And the tested refrigerants include R134A as a baseline refrigerant, with other refrigerant compared are R513A, R450A, R515B, R1234YF, and Turn 1. Next video, we will also test some high pressure refrigerant like R410A and its candidate replacements like R32, R452B and R454B. So tune in and also watch our next video regarding the high pressure refrigerant R410 and its replacement. So the measured data in this experiment is cooling capacity, COP, superheat, subcooling, pressure drops, etc. So here is the actual experimental test rig used for the experimentation, and this setup measures refrigerant pressures, temperature, mass flow rate to give us the real performance data. In this case, the refrigerant used was R134A and the cycle was tested under the controlled conditions. So the process of validation goes like this. We first gather the experimental baseline data. In our case is for R134A, which is a favorite medium pressure refrigerant. And then what we do, we run the simulation with the same input conditions and compare the results such as saturation temperatures of evaporator, condenser, temperature and pressure state points, cooling capacity, compressor work and COP, etc. And if they match closely, the model is validated. If not, we have to refine and repeat our simulation. So this loop makes sure we are not blindly trusting the software. And if our simulation model stays within 5% of the experimental data, then we can say that it is a reliable simulation model. From validation to optimization. Validation gives us the confidence. Once validation is successful, we can confidently move towards the optimization. This means that tweaking design parameters like the heat transfer fluid temperatures, superheating, subcooling temperatures, circuitry optimization, or refrigerant change so to maximize the efficiency and evaluate the performance virtually without needing hundreds of lab experiments. And here's the exciting part that optimization without validation is just a guess, but optimization with validation is a powerful design tool. So our goal is to find the best low GWP replacement for R134A in this video. So these are the points that are evaluated from the experiment, and we will put these experimental validated points in the impose mode to impose the geometry of the experiment, and then we will simulate it for different conditions for different refrigerants, and we will find out the real result. At last, we make comparison plot like this where we can compare the COP versus the cooling capacity and can easily compare different refrigerants and their performance in HVAC or any refrigeration system. So now let's move towards our simulation software and just input this data into it into the impose mode so that we can validate it, and then we will do our optimization. So first what we have to do, we have to put this data provided in that document into the software. So let's move on to our software, that is Cycle DHX. So for that you have to open the Cycle DHX version 2 and you have to open a new file. So what we are going to do, we have to select a single compound refrigerant, that is R134A in our case, for the baseline impose mode simulation, and in the cycle option we will select single stage, which does not include liquid line, suction line, heat exchanger, and in the cycle specification we will check for establish the reference parameters, and now I will input all the required parameters given from the experimental model. So now I have updated all the data from that experimental data points, and now what we will do, we will run it into the impose mode. Here we can see it has already run into the impose mode and it has imposed all the experimental geometry into this simulation, and the next step is now to run it into the simulate mode. It has also evaluated the reference parameters and the heat exchanger parameters from our baseline, that is our 134A. Now we will move towards the simulate mode. and now you can see it has simulated it, and now we have to check it, that is it giving us the correct data as of the experimental data. So what we will do, we will see the results. In the results we will go for the COP of cooling, and we will see the cooling capacity, and we will compare these values with the experimental data given. For example, here we can see that the cooling COP value is 5.80 at the capacity of 1.5. So here we can see at the capacity of 1.5 or 134A, experimental data points are showing COP value around 6 to 5.8. So here we can see our COP value is 5.8 at the cooling capacity of 1.5. So this is how validation works. Now we have simulated, or we have validated our simulation model with the experimental data, and it is giving us the correct results. So this is how the validation work. Now our model is validated with the experimental data. Now what we can do? Now we can change the refrigerants. Other things we can do, we can change the heat transfer fluid temperatures, inlet and outlet temperature in the evaporator and the condenser. We can change the superheat and subcool, and we can change the cooling capacity. So anything we can change. Now our model is validated. But just to see and compare it with this article, what we have to do, we can see that it has validated this baseline R134A, and then it has run it with the different refrigerant and compare its COP and capacity values. So now what we will do, we will run it for different refrigerant, and we will see that using the experimental validation data of R134A and validating it with experimental data, can we optimize this simulation tool for the other refrigerant also, and does it fit with the experimental results with these refrigerants? After running the R134A into the simulate mode, now what we are going to do, we are going to change the refrigerant, and we are going to check that the other refrigerants also give the desired optimization result. So for that, what we are going to do, we are first going to go to the refrigerant, and we are going to run it for R1234YF. So here we will select R1234YF, we will come back to cycle simulation, and here what we will do, we will now select optimize number of circuits. So now it will optimize the number of circuits based on the changed refrigerant, and it will improve the COP of it. And now we will run the simulation. So here are the results for R1234YF, and now we will see what are its COP value and what is its corresponding cooling capacity. So at the cooling capacity of 1.5, it is giving the COP value of 5.79. So here at the 1.5 cooling capacity, we can see this pink line are showing R1234YF data, and it is giving the experimental value of around 5.5, but the simulation values is a bit higher than it, which is around 5.6 or 5.7. So this shows that the results are within the error of 5%. Now we will move on, and we will test it for another refrigerant, that is R513A. For that we will move back to the refrigerant, we will go to the predefined blends, and here we will select R513A. So here is our 513A. We will select it, go back to the cycle specification, and then we will simulate it again. So here are the results of our 513A, and we will just see what is the COP of cooling value with cooling capacity of 1.5. It is giving COP of cooling value of 5.852. So here we can see our 513A results are given in red color, and at the capacity of 1.5 we can see the experimental result is around 5.6 COP. So we can see it is giving the value of 5.8, which is a little bit more than the experimental results, but it is still in the range of 5% error. So this shows that all these refrigerant and optimization is correct and under the error percentage of 5%, which is quite well. So this is how we can just change the refrigerants, and after running it into the impose mode we can simulate it with different refrigerant, and it will give you quite better results which are quite near to the experimental results. So this is how the validation works and optimization works after a experimental validated simulation model. So the example results show that the COP prediction error was only 0 to 3%, and the cooling capacity prediction error was within 5%. So our model successfully ranked the refrigerant in the same order as the experiment was showing. Like the high COP refrigerant were on the top, and then the low COP refrigerants were showing trend on the bottom. So the trend was same as in the experiment. So the key takeaways from this video, we can say that the validation bridges the gap between the theory and the reality, and it ensures that the cycle DHX predictions are trustworthy. They are just not a simulation results, but these are the results which you can trust and you can believe, because these are the real cycle results which you can get from any experimental data. And it enables us a low cost refrigerant screening for our research purpose, for our study purpose. You can just validate your simulation first in the impose mode, and then you can use it as per your requirement for other refrigerants, for other conditions, for other cooling capacities, and it is essential before performing optimization study. So validation is always the first thing you have to do before doing the optimization, because without validation the optimization results are not valuable. So this is all for this video. If you like this video, please like and subscribe my channel, because this is the only way for motivating me for making more such videos. So thank you very much.